Welcome, curious minds, to another deep dive. Have you ever really thought about balance? Not, just something perfectly still, like a statue. I mean, something more dynamic. Think about a football game. You've got, 11 players per side on the field. That number stays the same, but the players themselves, constantly swapping out, moving around. It's balanced, but it's definitely not static. Or even simpler, think about a closed water bottle. Water evaporates, water condenses. The amount of vapor in there hits a steady point, but molecules are always jumping between liquid and gas. Dynamic balance. So, what if chemical reactions work the same way? Deep down at the molecular level, they find this incredible balance too, not by stopping, but by the forward and reverse happening at the exact same pace. Today, our mission is to really unpack this fascinating world of chemical equilibrium. We'll explore how reactions reach the state where everything looks constant, but trust me, there's a whole lot of action still going on. We're diving into the core ideas from chemistry, the central science, looking at real-world stuff and making sure this fundamental concept really clicks for you.
Exactly. Our goal here is to demystify this. It's absolutely critical in chemistry. We'll cover what it is, how we actually put a number on it, and maybe most importantly, how we can predict what will happen. And even how we can sort of nudge reactions in the direction we want. Get ready for hopefully, some real aha moments connecting chemistry to the world around us.
Okay, so this molecular dance, it's happening, but just knowing that isn't quite enough for a chemist, is it? We need to measure this stuff. How do you quantify that balance?
Right. So fundamentally, chemical equilibrium is reached when the forward reaction, that's reactants turning into products, and the reverse reaction, products turning back into reactants, happen at precisely the same speed. The rates are equal. This means the overall or net change in how much stuff you have, the concentrations, becomes zero.
So yeah, it looks like the reaction has just stopped.
Okay.
But it hasn't. It's just balanced, a constant molecular turn.
Let's make that really concrete. Your source has this classic example, colorless N2O4 gas turning into brown NO2 gas.
Wow.
Yes, the nitrogen tetroxide and nitrogen dioxide.
Right. So you seal some colorless N2O4 in a tube, maybe warm it up a bit, it starts turning brown. Then the brown color just stops getting darker. What's actually going on there? Did it just run out of steam? Or is something else happening?
That's a perfect example because it looks static, but it's absolutely not. The reaction is reversible. N2O4 gas can break apart into two molecules of NO2 gas, and two NO2s can bump into each other and reform N2O4. We write it with that double arrow. N2O4G equals 2 NO2G.
Okay.
At equilibrium, the speed at which N2O4 breaks down is exactly matched by the speed at which NO2 molecules recombine. So the brown color, which comes from the NO2, stays constant. But individual molecules are constantly swapping identities. It's truly dynamic. Forward rate equals reverse rate.
Got it. So the big takeaway, concentrations become constant, yes, but it's in a closed system, and the reaction is still humming along in both directions. Dynamic, not static. Okay, now we understand the what. How do chemists put a number on it, quantify that balance point?
Well, this takes us to the law of mass action. This was figured out way back in 1864 by Goldberg and Wage. It gives us a mathematical way to describe the ratio of products to reactants at equilibrium. For a general reaction, say little a moles of reactant, A plus B moles of B, go to D moles of product D plus E moles of E, so AA plus BB, B plus DD plus EE.
Right.
The equilibrium constant, which we call Kc, the C stands for concentration, is calculated like this. You take the concentrations of the products, each raised to the power of its coefficient in the balanced equation.
Okay, so D to the power D, E to the power E.
Exactly. And you divide that by the concentrations of the reactants, also raised to their coefficients. So A to the A, B to the B. That expression, Kc, XD, DD, AD, gives you a specific number that represents the equilibrium position at a certain temperature.
A snapshot of the ratio. Okay. Now, let's connect this to the real world. Your sources mention the Haber process for making ammonia. N2 gas plus 3H2 gas makes 2 NH3 gas. This one reaction, it's huge, isn't it? It's got this incredible story behind it, feeding billions, but also, playing a role in war. How does one reaction carry so much weight?
It's absolutely foundational. Ammonia is the key ingredient for nitrogen fertilizers. Without the Haber process, feeding the current global population would be, basically impossible. Crop yields depend heavily on it.
Wow.
But yeah, the history is complex. Fritz Haber developed it around 1912. Carl Bosch figured out how to do it on an industrial scale. And during World War I, Germany's access to natural nitrates needed for explosives was cut off. The Haber-Bosch process allowed them to make ammonia from air, then nitrates, keeping their munitions production going. Some argue it prolonged the war.
Right.
But then Haber himself, brilliant chemist, got the Nobel Prize for this work. But he was also deeply involved in developing chemical weapons later, which obviously casts a shadow It really highlights how science can be used for vastly different ends.
A really powerful example. Okay, back to the chemistry. This Kc value, this equilibrium constant,
Hmm.
it really is constant for a specific temperature, right? Doesn't matter how you start the reaction.
Precisely. You could start with only N2 and H2, or only NH3, or some random mix. If you let it reach equilibrium at a certain temperature, the ratio described by Casey will always be the same. The N2O4-NO2 example you mentioned. The textbook data shows that whether they started with pure N2O4 or pure NO2, once it settled, the Kc value consistently came out around 0.212 at that temperature. The system finds that balance.
That's quite something. And you mentioned Kc uses concentrations. What about gases? Isn't pressure more common?
Good point. For gas phase reactions, we often use Kc, where P stands for partial pressures. You calculate it the same way as Kc, but using the partial pressures of the gases instead of their molar concentrations. And there's a simple mathematical relationship between Kp and Kc using the ideal gas law. It involves the change in the number of moles of gas in the reaction, represented by Un. The formula is Kp equals Kcrt. You might also notice that we usually don't write units for K. Technically, it's because the expression uses something called activities, which are like effective concentrations or pressures relative to a standard state. This makes K dimensionless, a pure number. Helps compare different reactions.
Right, activities. Okay, so we have this number K. What does the size of K actually tell us? Is a big K good? A small K bad?
The size is incredibly informative. If K is large, let's say much greater than 1, K1, it means the equilibrium lies to the right,
Meaning?
meaning products dominate at equilibrium. You'll have much more product than reactant once the reaction settles. Your source gives the example COG plus CL2G. Its Kc is huge, like 4.56 by 109. That reaction strongly favors making the product, COCl2.
So if you want lots of product, big K is good.
Definitely. Conversely, if K is small, much less than 1, K1, the equilibrium lies to the left. That means reactants dominate. You won't get much product formed before equilibrium is reached.
Okay, that makes sense. Now, does it matter how we write the equation? If I flip it around, is K the same?
Absolutely crucial point. It matters a lot how you write it. The value of K is tied directly to the specific balanced equation you're using. If you reverse the equation, the new equilibrium constant, K is the reciprocal of the original. So KO2O1K, remember our N2O4 example, N2O4O2O2, NO2 had Kc equals 0.212. If we write the reverse, 2NO2 equals N2O4, the new Kc is 1.212, which is about 4.72.
Oh,
So you always have to specify the balanced equation when you give a K value. Always.
got it. What if you, say, double all the coefficients?
If you multiply all the coefficients in a balanced equation by some factor, let's say n, then the new equilibrium constant is the original K raised to the power of n. So new, original n.
Okay, power rule.
And one more. If you add two reactions together to get an overall reaction, you multiply their individual K values to get the K for the overall reaction. It's kind of like Hess's law for enthalpy, but with multiplication instead of addition.
Interesting connection. Okay, what about reactions that aren't just gases? What if you have solids or liquids involved? Do they just get ignored in the K expression?
That's called heterogeneous equilibria, when you have substances in different phases. And yes, pure solids and pure liquids are omitted from the equilibrium constant expression,
Why is that?
because their concentrations, or more accurately, their activities, are essentially constant. Think about the density of a solid block or a pure liquid. It doesn't change significantly even if the amount changes. Since K tracks the ratio of things whose concentrations can change as equilibrium is approached, the constant concentrations of solids and liquids get sort of absorbed into the value of K itself. Their activity is taken as one.
So they're there, but they don't affect the ratio calculation.
Exactly. For example, if you have solid calcium carbonate decomposing, CaCO3 is equal to CaO plus COT. The equilibrium expression is just KcCO2 or Kp equals PCO2. The solids don't appear. It simplifies things, but it's a key rule to remember.
Definitely a point to watch out for. Okay, so knowing K seems really powerful. It tells us where the balance lies. Can we use it to predict things? Like if I mix stuff together, can K tell me which way the reaction will go?
Absolutely, that's one of its main uses. First, if you know all the concentrations at equilibrium, calculating K is easy. Just plug the numbers into the expression we talked about.
Right.
But often you might know the initial amounts you put in and maybe measure just one concentration once it reaches equilibrium. From that, you can figure out K. This is where the ICE table comes in really handy. ICE stands for initial change equilibrium.
Okay, ICE table. How does that work?
You make a little table. First row is your initial concentrations. Second row is the change in concentrations needed to reach equilibrium. Often you use X based on the stoichiometry. Third row is the equilibrium concentration, which is just initial plus change.
I see.
So you set up the table, use the known equilibrium value to solve for x, figure out all the equilibrium concentrations, and then plug those into the Casey expression to calculate K. It's a standard problem-solving technique.
Okay, that sounds systematic. Now, what about predicting direction? Say I mix some reactants and products, but I don't know if it's reached equilibrium yet. How can I tell?
For that, we use something called the reaction quotient, Q.
Q, like K.
Exactly like K in form. You calculate Q, use the exact same expression as K, but you plug in the concentrations you have right now at any point in time, not necessarily at equilibrium.
Okay, so Q is like a snapshot. K is the destination.
Perfect analogy. Then you compare Q to K. If QK, your current ratio of products to reactants is too small. The reaction needs to shift, right? Make more products, use up reactants to reach the equilibrium ratio K.
Okay, Q less than K shifts right.
If QK, congratulations, your system is already at equilibrium. No net change will occur. And if QK, your product to reactant ratio is too high. The reaction needs to shift left, make more reactants, use up products to get back down to the equilibrium ratio K.
Q greater than K shifts left. Simple comparison. Got it.
It's a very useful tool for predicting reaction direction.
And the final piece. Can we use K to actually calculate all the equilibrium concentrations if we only know where we start?
Yes, that's often the ultimate goal. You know your initial concentrations and the value of K at that temperature. You set up your ICE table again, expressing the equilibrium concentrations in terms of X. Then you plug those equilibrium expressions with X in them into the K expression. This usually gives you an equation you need to solve for X. Sometimes it's straightforward, sometimes it involves solving a quadratic equation.
All the algebra returns.
It does.
Yeah.
But solving for X tells you exactly how much the concentrations changed, so you can calculate the exact amounts of everything present once equilibrium is established. It shows the real predictive power of K.
This is fascinating. So equilibrium isn't just a static endpoint. It's predictable, quantifiable, but can we influence it? If a reaction reaches equilibrium, can we, push it one way or the other, especially if we want more product, like in the Haber process?
Absolutely. And this is where Le Châtelier's principle comes in. It's a cornerstone of understanding equilibrium. Basically, it says, if you take a system that's already at equilibrium and you disturb it by changing concentration, pressure, or temperature, the system will shift its equilibrium position to try and counteract that disturbance.
It pushes back.
It pushes back. Chemistry's way of trying to restore balance, you could say.
Okay, let's break that down. First disturbance, changing concentrations. What if we just dump in more reactant? Or maybe pull out some product as it forms?
Great questions. If you add more reactant, the system says, whoa, too much reactant. And it shifts to the right to consume some of that added reactant and make more product.
Counteracting the addition.
Exactly. And if you remove a product, this is key industrially, the system says, hey, where did the product go? And it shifts to the right again, trying to replace the product that was removed. Think about the Haber process. N2 plus 3H2 equals 2NH3. If you continuously remove the ammonia, NH3, as it's made...
you force it to keep making more.
Precisely. Removing the product pulls the equilibrium constantly to the right, dramatically increasing the overall yield of ammonia. It's a clever application of the principle.
Very clever. But does this messing with concentrations change the actual value of K?
Excellent point. No, it does not.
Correct.
Changing concentrations shifts the position of the equilibrium, meaning the actual amounts of each substance change. But the ratio defined by K remains constant at that temperature. The system just finds a new set of concentrations that still satisfy the same K value.
Okay, K stays put. What about the next disturbance? Changing pressure or volume, especially for gases, if we squeeze the container.
For gas reactions, pressure and volume changes matter if the number of gas molecules changes during the reaction. If you decrease the volume, which increases the pressure, the system will shift in the direction that produces fewer moles of gas. Why?
Right.
To reduce the number of gas particles bouncing around, which helps to lower the pressure, counteracting your squeeze.
Okay, less volume, fewer gas moles.
Right. And if you increase the volume, decreasing pressure, the system shifts toward the side with more moles of gas, trying to fill that extra space and bump the pressure back up a bit.
So back to Haber. N2 plus 3H2 equals 2NH3. That's 4 moles of gas on the left, only 2 on the right.
Exactly. So if you increase the pressure, decrease volume, the equilibrium shifts to the right, favoring ammonia production, because that reduces the total number of gas molecules. High pressure is crucial for the Haber process yield.
Makes sense. What if the moles of gas are equal on both sides?
Then pressure changes have no effect on the equilibrium position. like H2 plus I2 equals 2HI. 2 moles of gas on each side. Squeezing it doesn't offer a relief direction. Oh, and one more thing. Adding an inert gas, like argon, at constant volume doesn't shift the equilibrium. It increases the total pressure, sure, but it doesn't change the partial pressures of the reacting gases, so K remains satisfied.
Important distinction. And again, does pressure change K itself?
Nope. Just like concentration changes, pressure volume changes shift the position, but do not alter the value of K at a given temperature.
Okay, K is proving quite resilient, but now the big one, changing temperature. Does K finally budge here?
Yes. Temperature is the one factor that changes the actual value of the equilibrium constant, K.
Uh-huh. How does that work?
The easiest way to think about it is to treat heat as a reactant or product. For an endothermic reaction, one that absorbs heat, heat is like a reactant. Reactants plus heat, products. If you increase the temperature, you're adding heat reactant. Le Châtelier says the system will shift right to consume that added heat, making more products. So for endothermic reactions, increasing T increases the value of K.
More heat drives it forward, bigger K.
Okay, your source mentions a cobalt complex that's pink in cold water and turns blue when heated. CoH262 plus pink plus Cl CoCl4 2 blue plus H2O. Heating shifts it right blue, meaning the forward reaction is endothermic and K increases with temperature.
Cool visual. What about exothermic reactions?
For exothermic reactions, ones that release heat, heat is like a product. Reactants, products plus heat. If you increase the temperature, you're adding heat product. The system shifts left to consume that heat, making more reactants. So for exothermic reactions, increasing T decreases the value of K.
Adding heat drives it backward, smaller K.
Precisely. Lowering the temperature would have the opposite effect in both cases. The deep reason is that temperature changes affect the rates of the forward and reverse reactions differently, because they usually have different activation energies. This unequal effect on rates changes their ratio, which is K equals K forward, reverse.
Okay, so temperature is the K changer. Last piece. Catalysts. We use them all the time. Do they shift equilibrium, change K?
Great question, and the answer is a clear no. Catalysts do not change the equilibrium position or the value of K.
So what do?
They speed things up. A catalyst lowers the activation energy barrier for both the forward and the reverse reactions, and it does so by the same amount.
Ah, equally for both directions.
Exactly. So both forward and reverse reactions get faster, but their ratio, which determines K, doesn't change. The result, the system reaches equilibrium much faster, but the final destination, the equilibrium composition, is exactly the same as it would be without the catalyst.
It's like paving the road, not changing the destination city.
Perfect analogy. You get there quicker, but you end up in the same place.
And this is vital for industry, right? Like back to Haber.
Absolutely critical. The Haber process equilibrium is actually more favorable at lower temperatures. Since it's exothermic, lower T means higher K. But at low temperatures, the reaction is incredibly slow. Finding a good catalyst was the breakthrough. It allowed the reaction to proceed at a reasonable rate at intermediate temperatures, a compromise between getting a decent equilibrium yield, K value, and getting it fast enough to be practical. Saved huge amounts of energy, too. Another great example is in catalytic converters in cars. Making nitric oxide, NO, is endothermic, so high engine temperatures favor its formation. That's bad. It's a pollutant.
Right.
When the exhaust cools, the NO decomposition back to N2 and O2 is slow. The catalytic converter contains catalysts like platinum, palladium, that speed up that decomposition reaction at exhaust temperatures, converting harmful NO back into harmless nitrogen and oxygen before it leaves the tailpipe. Brilliant chemistry at work.
Wow. Okay, we've really covered a lot. From just the idea of this dynamic balance, through quantifying it with K, predicting shifts with Q, and then manipulating it with Le Châtelier's principal concentration, pressure, temperature, catalysts, it really gives you a toolkit for understanding reactions.
It really does. And hopefully, you see, this isn't just abstract theory. It's fundamental to so many processes that shape our world, from making fertilizers and materials to controlling pollution. Understanding equilibrium is understanding a huge part of practical chemistry. This dive into chemistry, the central science, really lays that groundwork.
So maybe the next time you see something that looks perfectly still, whether it's chemical or not, perhaps pause and wonder, is it truly static? Or could there be a hidden dynamic equilibrium humming away beneath the surface, a constant dance maintaining that appearance of calm? Something to think about.